A diffraction grating has 2,450 lines per centimeter. It is illuminated by 632.8 nanometer light beam that is 1.7 millimeters wide. Oh, what angle separates the first order and the fifth order fringes? Okay, so we're going to use this guy here. Okay, now that whole 1.7 millimeters and whatever, we're going to get to that when we get to the resolvency here. Okay, but for number 4, we're going to do this, but we have to figure out what D is, right? So we know that 1 centimeter, though, is divided into that many spots, right? So D is going to be literally 0.01 meters divided by 2,450. So we can do that. Okay, that is 4.0816 times 10 to the minus 6th meters, which is pretty typical for the separation, right? You can barely see it. It's microns. And an approximation of this is if you look at the spacings on like a DVD or something like that, it's something like that, Okay, let's see. What angle separates the first and fifth order fringes? The first and fifth order. Okay, so we got to find 2 angles with this. Let's do this. Okay, so the first order, let's find the angle for the first order. The first order is going to be, where n is going to be 1, so we're going to go 1, because it's the first order. This times 632.8 times 10 to the minus 9th. Okay, that equals D, which is 4.0816 times 10 to the minus 6th times sine of theta, right? So to find theta, it's going to be the inverse sine of this times this divided by this. I can do this. All right, so second sine, 1 times 4.0, whoops, what am I doing? 1 times 632.8 times 10 to the minus 9th divided by that number, right parenthesis. I've got it. All right, are we ready for this? And these angles, by the way, these angles are too big to use, like, the approximate formula. Okay, I'm just going to say. All right, so that angle, that theta, is equal to 8.919, we'll say, degrees, right? And then let's find the fifth order fringe. Fifth. 5 times 632. And that's all you do. Like, this is the order. N is the order of the fringes. Okay. Times 10 to the minus 9th equals 4.0816 times 10 to the minus 6th sine of theta, right? So we plug that in. Now, literally, I'm just going to go up arrow. I'm going to grab that thing and change my 1 to a 5. And I got 50.82. So theta equals 50.821. Okay, so the angle between, the difference in angle is just we subtract the angles, right? So I'm going to go 50.821 minus 8.919. So minus, and I get 41.9 degrees. That's about as hard as you can make a diffraction grating problem. Okay. So now let's look at the what is the closest shorter wavelength that can be resolved in the first order with this diffraction grating. Whoa, it's going to be tough. Okay, I'm erasing. Are we ready for this? Okay. So now we're going to use this resolvency, right? So the wavelength is to this, right, is equal to the order. So M is 1. So the order times the number of lines that are illuminated, right? So the question is, how many lines are illuminated, okay? How to do that? There's two ways to do that. One way is to just use direct proportions, right? There's 2,450 lines per centimeter, right? But the beam is only 1.7 millimeters wide, okay? So the number that are illuminated, we know that 1 centimeter is 2,450. So 0.17 centimeters is how many? Okay, so we could do a proportion like that, right? If I do that, I get 0.17 times 2,450 divided by 1. I get 416.5. Now, what does that mean? I just don't know. How can you have a half a thing illuminated? But I'm not going to mess with that, okay? So that's one way to do it. The other way to do it, by the way, is to take a centimeter, or take a 0.17 centimeters, or 1.7 millimeters. I can go 1.7 times 10 to the minus third, and I could divide it by the width of those slits, right? I'll get the same number. So 1.7 times 10 to the minus third divided by, and then I have to find that number. What is that? It was small. There it is. Divided by 4. Remember these slits, the D that we figured out in the first part of this problem is 4.0816 times 10 to the minus 6. So this might make more sense to you rather than use a proportion, right? Okay, so if I do that, I also get 416.5. So that is my N. Oh, this should have been an N. N. There. Okay. Okay, so now we're ready to go. We're ready to rock and roll. Okay, our wavelength is 632.8 times 10 to the minus 9th meters. Actually, you know what? I'm just going to leave it like that. Okay, divided by delta wavelength is equal to 1 times 416.5. Okay. And now I can figure out my difference in wavelength. And since I'm just putting nanometers in, it's going to be in nanometers. Okay. So my difference in wavelength is literally just this divided by that. Okay, so 632.8 divided by 416.5 is 1.519 nanometers. Since I put nanometers in, I'm going to get nanometers, right? Okay. And this is, what is the closest shorter wavelength that can be resolved? Well, shorter would be just less, right? So the wavelength, the shorter wavelength, I'll call it lambda s, okay, is going to just be 632.8 minus 1.519. 632.8 minus that number we just got. 631.28 is what I'm getting nanometers. So if it was that close, if you had a wavelength that close, you could actually resolve it. Because when you look at these diffraction patterns, they kind of look like this. It's like, and the question is, you have another line, and it's so close. Is it actually 2 lines or 1 line, right? Okay. Remember that the more slits you have illuminated, the sharper these lines are, right? Okay. So in the case of not enough slits, you've got this big, wide, sort of fuzzy peak, right? And then you've got another big, wide, fuzzy peak like that. And they're so close to each other, you can't, it's like, is it 2 or is it, okay. And that's what they're dealing with, like with this. Okay. Yeah. All right.